In this lesson, we're going to define and talk about magnetic flux, and then we're going to use that to describe Lenz's law. So to think about flux, let's think about an analogy using a fan. Imagine we have a rectangular wire in front of a fan that's blowing air, and we can change the angle of that rectangular wire. If you want to get the most air blown through the loop, or the loop of wire, you're going to hold the loop perpendicular to the fan. So you could hold it this way or you could hold it at an angle, but if you want to get more air traveling through it, you're going to hold it perpendicular to the fan. If you turn the loop sideways, less air will blow through at an angle. The effective area of the loop has been reduced, and the effective area is the area right here, the area that air will blow through. We're going to consider this similar idea with magnetic fields. So let's say we have a constant magnetic field. In this case, it's going to the right, and we have a loop that is perpendicular to the magnetic field. For the most magnetic field to pass through the loop should be perpendicular. If I put it at an angle, I will have less magnetic field traveling through the loop. So if a loop of an area A, so let's say this loop from the side has area A, is tipped at an angle theta from the perpendicular. So here I tip it at an angle of theta. The effective area, or the area that a magnetic field goes through, is going to be defined as A times cosine of theta. So the amount of magnetic field that goes through the loop is going to be defined as the magnetic flux, and that depends on that effective area. Magnetic flux is just basically how much magnetic field is getting through the loop. So if it were perpendicular, we would have a lot more magnetic field going through, and if it's turned at an angle, we have less magnetic field going through, so we would have less magnetic flux. So the magnetic flux equation, and this is on your equation sheet, we have two versions of it. It is the dot product of the magnetic field vector and the area vector. And the simplified version that we're going to be using for our calculations is the magnetic field is equal to the magnitude of the magnetic flux is equal to the magnitude of the magnetic field times the cosine of the angle times the magnitude of the area. So in this case, magnetic flux is, we represent it with the Greek letter phi, and the units for flux are Webers, and a Weber is equal to 1 Tesla times a meter squared. And you can see that from the equation. This is the Tesla, and area is a meter squared, and that gives us the units for flux. So B is our magnetic field in Teslas, A is our effective area in meters squared. In this second equation, the magnitude sign says that we're looking at the magnitude of the magnetic field and magnitude of the loop area. Theta is the angle between the loop and the perpendicular. So this is the equation we're going to be using for our calculations. If you understand what a dot product is, this equation will lead to this equation also. So let's do a problem. Let's say we have 4 different circular loops that are perpendicular to the page, so we're looking at them sideways. Loops 1 and loop 2 have smaller radiuses, and loop 3 and loop 4 have radiuses that are twice that of loops 1 and 2. But the magnetic field B is the same for all of them. We want to figure out how do the magnetic fluxes compare between 1, 2, 3, and 4. So if you look at these, you may have an idea that, well, for example, you know that loop 4 probably has the smallest magnetic flux because it's turned completely parallel to the magnetic field and no magnetic field is going through it. But let's go through in detail the calculations for the flux for each of these. So we're going to be using this equation to find our magnetic flux. To do that, we're going to need to know what the area is of these loops. These are circular loops, so our area equation is pi r squared. For each of them, we're going to calculate the flux. The flux is equal to, and I just rearranged this equation, the magnitude of the area times the magnitude of the magnetic field, which we said was the same for all of them, times the cosine of the angle. So for the first one, we have pi, and we're going to say the radius of the first two is 1, and then the radius of the second two, which we know were doubled, is going to be 2 times 1, which is just 2. Oops. So the area of the first one is pi r squared times the magnitude of the magnetic field, it was given as B, times the cosine of the angle. The angle in this case is going to be 0, and cosine of 0 is 1. So this gives me a flux for the first one of pi times B. We don't know the value of B, so we can leave it as a variable. For the second one, we have the same area, but now we have an angle of 45 degrees, which gives me a 0.707 on the front. And it ends up as 0.707 times pi times B. Well, that basically is the same as 0.707 times the flux of the first one. For the third one, our angle is the same as the second one, but now we have a larger radius. So when we simplify it, we get to 2.83 times pi times b. And remember, pi times b is the flux of the first one. So this is 2.83 times the flux of the first one. And finally, for the fourth one, and we kind of could observe this just by looking, the angle is 90 degrees, the cosine of 90 is 0, so the flux through the fourth one is 0. So we're supposed to rate these in order of increasing flux or decreasing flux. We have the flux at 3 is the greatest. It's 2.83 times the flux of the first one. Then the flux of 1, because that's just the flux of the first one. Then the flux of 2, which is less than 1 times the first one, is 0.707. And then the smallest one is loop 4. So that's your final answer. Well, now that we've talked about what flux is, flux being the amount of magnetic field that goes through an area, we're going to use that to talk about Lenz's law. Lenz basically took the idea of an induced current and figured out exactly some more details about it. So Lenz's law says there is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. The direction of the induced, so that's the first part of Lenz's law. The second part says the direction of the induced current is such that the induced magnetic field opposes the change in the flux. Lenz's law is a little bit tricky. We're going to go through it in a few examples. Basically, we're going to create a changing flux in our loop. We can create a changing flux several ways. Basically, we either need to change the area, the angle, or the magnetic field. So for a changing flux, we can either change the magnetic field through the loop. So if I move a magnet towards the loop, I'm going to change my magnetic field. Or if I move it away, I'm going to change the magnetic field. So an increasing or decreasing magnetic field will change the flux. We can also have the loop area or angle changing. So I could make this loop smaller, or I could turn it at an angle so that the flux decreases or increases. And finally, the loop could move into or out of the magnetic field. So if I take the loop and pull it away from the magnet, I'm going to have a decreasing flux. If I move the loop, let's say to the side, I may have a decreasing flux. All right, so Lenz's law is a bit tricky. We're going to go through a few examples. Some big ideas you should understand. If the flux through the loop changes, we get a current. So we change the flux through a loop, we're going to induce a current. That current is going to, anytime we've created a current, now we're going to have our own magnetic field. So we have an induced magnetic field as a result of the induced current. The induced magnetic field is going to try to oppose the change in flux. Basically, you can think of it as the system wants to return to an equilibrium state or to its original state. So whatever kind of flux is, let's say we have an increased flux, we're going to create a magnetic field that opposes it to try to decrease that flux again. So we're going to do some examples. Let's consider a magnet that's at rest above a coil of wire. And it has a flux going downward through the coil. And right now there's no current because there's no change in flux, just a constant flux. If I move the magnet towards the wire, it's going to increase the downward flux. Increase the downward flux through the coil. Now, I have an increasing flux and I have a current. So what's going to happen is that the loop is going to want to counteract that changing flux by creating an upward pointing field to oppose the change. So we have an increased flux downward, so the response of the wire will be to create a magnetic field going upward. So to create a magnetic field going upward, you use your right-hand rule, and you see that we have to create a current that goes counterclockwise to create an upward pointing magnetic field. So the response of an increased flux in this wire is an induced current that goes counterclockwise, and it does that, and as a result creates a magnetic field going upward, which counteracts the increasing flux. We could also have a magnet that's moving upward. If I have a magnet moving upward, I have a flux that is decreasing. If my flux is decreasing, the wire is going to create a magnetic field that will counteract the decreasing flux. So it's going to try to create more flux going downward. Because our flux is decreasing, the wire is going to try to make up for it by creating its own magnetic field. So to create a magnetic field going downward, using your right-hand rule, you're going to create a current that is going clockwise. Your clockwise current creates a downward magnetic field, and that opposes the change in flux. So we have now an induced current that's going clockwise. So you can compare these two. The decreasing flux created, in this case, a clockwise current, and an increasing flux created a counterclockwise current. So we're going to do lots of practice with which direction the current goes to counteract the change in flux. Here's our first example. A magnetic field goes through a loop of wire as below, and you can see it has X's, which means the magnetic field is going into the paper, or into the screen. If the magnitude of the magnetic field is increasing, what can we say about the current in the loop? So we have a flux that is increasing into the paper. Well, let's look at it step by step. First, what direction is the applied magnetic field? Based on the X's, it is into the page. Next, how is the flux changing? Well, we said that it is increasing. Now we're going to determine the direction of the induced magnetic field, and it's going to oppose the change in flux. So we have into the page and increasing. We want to oppose that. So opposing a change in flux into the page, our induced magnetic field is going to come out of the page. Now we're going to use our right-hand rule to find how to create a magnetic field that goes out of the page. The current to create a magnetic field out of the page, if you use your right-hand rule, it's going to go counterclockwise. And so that's the direction of the induced current in the loop. Let's do another example. A magnetic field goes through a loop of wire as below. If the magnitude of the magnetic field is decreasing, what can we say about the current? So we have magnetic field. First, the direction of the applied magnetic field, it's into the page because it has X's, and that says into the page. How is the flux changing? We said that it was decreasing. So instead of increasing into the page, we are decreasing, so it's reducing. The direction of the magnetic field to oppose a decreasing flux, we want our induced field is going to prevent it from decreasing, so that means our induced field has to go into the page also. It's going into the page to keep the overall flux from changing, because the flux was going into the page but getting less, so our induced one is also going to go into the page. So now we're going to use our right-hand rule. Which direction does the current go so that we create a magnetic field into the page? Our current is going to go clockwise to create a magnetic field going into the page. All right, our final example. A magnetic field goes through a loop of wire as below. If the magnitude of the magnetic field is not changing, what can we say about the current in the loop? Well, the direction of the applied magnetic field is into the page. How is the flux changing? It's not changing. The induced magnetic field is going to oppose the change in flux. Well, there is no change in flux. The change in flux is 0, so there's going to be no induced magnetic field. So what do we know about the current in the loop? There must be no induced current. If there's nothing to counteract, we're not going to create a current. So with a constant magnetic field, we will have no induced current.